Hi, so this is our project for EE3. It is a robot sensing car. What it does is it's a car that drives forward, and on the right and left side we have sensors that detect if there's a wall. If there is a wall, it'll turn away from it. After we completed all the hardware, which you can see here is an Arduino, an H-bridge, and two sensors, we then started working on the coding. The first thing to do was just to make it go forward. As you can see here, it goes forward, and the sensors do not work. One thing we noticed when we were first testing this is that the car is going a little bit to the left. This is because the battery is plugged into the right side before the left side, making the right wheel a little bit more stronger. Here you can see it happen. The next thing we wanted to work on was making the sensors have an input on the direction of the car. This was one of the most challenging parts of the project, the interactions between the sensors and the motor. The Arduino helps with this and really acts as the agent to combine the two, as the code lets the hardware interact with each other. The first sensor that we just saw worked by, once it was triggered, the car would move away at a set pace. We wanted to improve the sensors by making however close your hand is, the car would move away at a faster pace. So if something is 1 centimeter away, it'll turn much more rapidly than if something is 5 centimeters away. You can see here that as I put my hand really close, the car almost has a complete turn. The numbers that we assign to the turning are a bit arbitrary, and you can tell this when the battery dies. The car sometimes doesn't act as you want it to act. For instance, a sharp turn doesn't become a sharp turn, and full speed is pretty slow. Once we finished the basic sensors from our car, we wanted to move on to bigger things. So we went to IEEE and used their test track in order to test our car. It was very difficult at first. Our car was able to go through the straight edges, but as soon as we hit a curve, it would want to go into the corner. The reason behind this is the curves aren't in equal distance, so it required a lot more dynamic coding than we thought it would. Again, here you can see that the left distance is really great, so it goes into the curve. Eventually though, what we found to do was when it senses the open right side, it'll make a complete turn. Here it's going forward, correcting itself using a PID controller, well, only the P part proportion. And right there, when the LED goes off on the car, it means it's going into a open loop-like solution where it turns right for a set duration of time and assumes it'll make a complete right turn. It does the same for left. In this first test, you can see that our PID is not good because it only has proportion. The car is overcorrecting itself and very wobbly. Our car here was able to finish the maze, but we still wanted to work on it to be more stable. We did this by adding the derivative part. Derivative helps prevent future error. By doing this, once the car veered off, when it veered back on, it wouldn't continue to go right and left. There are many variables when we were working with this that we didn't expect. For instance, the tape caused our car to stop a couple times, and also the sunlight would affect our car. In this turn, you're going to see the power of the derivative. Unlike the other turn, where it kept on wobbling, our car was able to straighten out after just 2 small turns. This PID controller with just proportion and derivative was very effective for us. Our car didn't completely complete this maze, but we were really happy that the derivative part of our controller worked. After much refining, we were able to have our best run when we completed the course in 26 seconds. This was done by pushing the car speed to the max, so it could barely be able to sense the turns in time. The main way we were able to increase speed, however, was letting the car go fast on straightaways. We did this by seeing the difference in between the right and left sensor, and we chose a small value and decided that if the distance is in that small value, the car can speed up because there's no turns coming up. Thanks for watching, and thanks to IEEE for helping us out with the project.